Hello and welcome to the second episode of Code Deep Dive. In the last episode, I showed how standard vector is designed in C++. In this episode, let's see what happens when we start adding elements to the vector. We know that standard vector inherits from vector base and contains vector imp, which stores pointers in vector imp data and also handles data allocation. Let's start from adding the first element to the empty vector object. I will put breakpoint on pushback. Let's deep dive. We are adding our value to the vector and pushback method is delegating add operation to emplaceback. Emplaceback checks first if finish pointer and storage point match. We see that in the newly allocated vector, all pointers are null. On match, some allocation is performed. Let's deep dive. We will skip forward invocation for now, and iterator pointing to the end of an array is created. A couple of things happen in the realloc insert. First, there is a check on some length. In the first step, maximum available allocation size is checked. This requires allocator object, which is represented by vector imp object. Two things are collected: maximum value from pointer difference in GCC divided by the size of the type in bytes. In this case, for my machine it's 4. For integer value, it's maximum count of integers. The second value is maximum number of elements that can be allocated by allocator. The check is therefore to be sure we don't request memory allocation for more elements that could be provided. Since this is passing, there's a calculation of the difference between array finish and start pointer. The size type is just a size t. As the vector is still empty, the difference is 0. Since size is called twice, it's expected to double size of an array, with exception to empty vector. In such case, the size is simply 1. There are also additional checks to ensure that the allocation does not go beyond maximum available allocation. This len variable is the new size of the vector. Then, all pointers are recorded and also current number of elements is computed from the difference of iterators. There are 0 elements, as you can see. In the next step, I expect the allocation will happen of len elements and the type pointer is integer pointer. This function uses memp, which is allocator with this in this implementation. Since the requested value is greater than 0, this ultimately delegates to allocator. This is new allocator implementation. There is this condition here with GCC compiler expression that checks again if the request does not exceed the allocation limit. This is usually not the case, so the built-in expect allows some CPU optimization here. In the end, allocation is delegated to C++ new operator with this GCC macro. We are not going to go deeper from here, as it's much beyond the scope. The request is about n elements of specific size, which is about memory size in bytes. Let's go back. There's a new memory address, but there's nothing relevant there yet, and all zeros in this particular case. Let's deep dive into construct. This construct method belongs to allocator object. In this call, pointer of newly allocated memory is passed and new operator is called. This new operator returns pointer as it is. It's because we have already allocated memory and now we are going to put data there directly. In this place, a UP constructor is called. Let's get back. To summarize, here we stored old memory locations, and we also have new memory location allocated upfront to store amount of data we are adding and already existing data. Next, we created objects on the heap in the newly allocated area. The last part is about moving existing data into the new area. As soon as it's done, the last thing to do is to deallocate old memory. As vector is empty, nothing has to be done. Vector imp is finally updated with new memory locations. We can see that value 1 is stored in the start address, occupying 4 bytes. The end of a vector matches end of the memory. The operation has completed and there's vector with 1 element. We learned that this implementation doubles size of the memory if there's no more room for new elements. When pushing another value, the vector size should be 2. Let's add 2 more elements and see what happens. There are 3 elements in the memory, 4 bytes each. Finish pointer indicates there is space for 1 more element. This time, emPlaceBack constructs object directly on the heap, since there is free space available. Finish pointer should move forward by 1 element. Let's refresh the view. Here's the 4th element. So far we have been working with R values. Let's see what happens when pushing L value. I will push back 2 additional elements to the existing vector. This operation is handled by overloaded pushback method. Vector is already at capacity, therefore realloc insert is as well overloaded. The only difference will be that at time of construct, copying constructor is called instead of the move constructor. In case there is no need to grow memory, a new element is constructed immediately in the free space. To summarize, pushing back elements to vector consists of the following phases. Firstly, we make sure we have enough capacity. If not, new memory is allocated by doubling size of the current memory. The content of the old memory is moved to the newly allocated memory. Secondly, the new element is constructed directly on the heap. Finally, old memory is released. As long as vector has capacity, pushing back new element runs in constant time. In the next video, let's see how vector properties are computed.